Hello, Lewis. How are you?
Hi, John. How are you doing?
I'm doing well. How are you?
Good. Yeah. Everything's been going a little bit slower, so I'm a little like, oh, this was unexpected,
Yeah.
How are you doing? Last week you said you had COVID. Are you feeling better?
I'm feeling all.
Yeah, we have this interesting project. It'd be fun to talk with you about it sometime.
Cool. Yeah, definitely.
About Benjamini-Schramm limits of random translation surfaces.
Oh, that's really cool. I think the question of random translation surfaces and random Riemann surfaces is really interesting.
I'm sure, speaking for Hunter and myself, we'd love to talk with you about
it. Yeah, that'd be great.
Yeah, it's not really something I've thought about, but I think it's a supernatural question. I think there's a lot open there, and I think it's super cool. So I'm glad you guys are looking into it. And I would really be happy to talk about it. So if you want to schedule a time or something, I'd really be happy to.
Absolutely. Yeah.
Yeah, that'd be great.
But just a warning, I haven't really thought about it at all. So, but
that's good. That's even better. You have some fresh eyes on it. I feel like we should wait a couple of minutes because we usually have a larger crowd, although it's an unusual time,
Yeah. Hi, Amanda. Where are you these days?
Hi, I'm at UT.
Oh, cool. Nice. How do you like Austin?
I like it. Yeah. I grew up in Wisconsin, so I'm getting used to the weather, but I was in Kansas for 6 years, so it was sort of, I guess, in preparation.
It was absolutely beautiful this morning. Nice and breezy. I don't know how, it's supposed to be nice tomorrow too, I think, but then it's supposed to heat up in the weekend.
I don't know how anybody else feels, but I grew up in the Northeast and then I went to grad school in Houston. And my feeling was it's better to be hot than cold.
I disagree.
Okay.
I'm from Pennsylvania, so and I'm a second-year student, so I've been in Texas for like 15 months now, and I hated it at first, but then like recently I've realized that 90 degrees just doesn't feel that hot to me anymore, and my life has gotten a lot better.
It's always sunny, almost always.
Yeah, that's true. It was very cloudy where I grew up.
Yeah, unless it's spring, then it rains for a whole month.
I think it's time to get started. Are you, would you like to get started, John?
Sure thing. So let me start by saying that I'm bad at monitoring the chat when I'm giving talks. So please feel free to just speak up, or if you see something in the chat that hasn't been responded to and that I should answer, please draw my attention to it. Okay, so this is, so this talk today, what I want to do is I want to talk about something called the Horocycle flow on strata of translation surfaces, which is a dynamical system that is an important one to study. It's really interesting and very little is known about it. So I'm kind of excited about what we showed, but there's a lot of other questions still available about this system. And I think it's a really interesting thing for other people to study. I think it's a great area to go into. So I want to define all of the terms. So let's start off with what a translation surface is.
Can we ask before you start?
Sure.
Does this have anything to do with horocycles?
Yes.
Because horocycles are on the Poincare disk and are big round circles.
Yeah, so the horocycle flow on the Poincare disk could be studied from the standpoint of wanting to study constant curvature flows. And I guess the horocycle flow is constant curvature -1. So this is the setup that Hedlund does when he originally institutes it. This is the same thing for a generalization of this space, which is the space of Riemann surfaces, with the generalization of that metric, which is the type Mueller metric.
So, but I mean, so this would be Horocycle for type Mueller metric or for the flat surface?
For the type Mueller metric, and it is the flat surface.
Okay, thanks.
Okay, so it also, you can view this as also, so we're going to see in a little bit that you could view this also as being the action of a subgroup of SL2R on this space. And this Horocycle flow is the action of SL2R on the same, on a different space, the same subgroup of SL2R on a different space. And tying in what you were saying to before, whether the relationship between flat surfaces and Riemann surfaces, really this is taking place in the unit tangent bundle to the space of Riemann surfaces, which is morally the space of flat surfaces, depending on what you mean by flat surfaces.
Okay.
Did I answer your question, Steve, or did I dodge it?
You kind of dodged it because I didn't get any pictures.
Oh, the pictures are coming.
Yeah, I know. Yeah, so no, thank you. Yeah.
Okay, cool. All right, thanks. Any other questions at this point? Great. Okay, so let's begin with what a translation surface is. So what's the starting point? We have a compact genus G Riemann surface, and we want to give it another additional structure on it. So we want to give it a flat metric. So this is a metric in the conformal class that gives you this Riemann surface, which is locally Euclidean. And moreover, I want the transition functions between charts to be translations, except at finitely many points, which are going to be cone points of integer multiple of 2 pi n, because you can't have an everywhere flat structure on a compact Riemann surface of genus bigger than 1 by Gauss-Bonnet. Okay, so the negative curvature needs to live somewhere, and the flat structure concentrates it at cone points. Let me emphasize, and this is connected to what Steve was asking, that this is more than just a Riemann surface. This is a Riemann surface with an additional metric in its conformal class, and Riemann surfaces will have multiple, will have many such metrics on them. Okay. Now, as is often the case, a picture is worth at least 1,000 words. So let's draw a picture of what this is, or let's show a picture of what this is. So this is a translation surface. So what have I done? I've drawn for you one of these charts. And what do I mean by the transition functions between charts or translations? The sides that are parallel and of equal length and have the same color are identified. So blue is identified with blue, red is identified with red, orange is identified with orange, and black is identified with black. And so when I move off of the chart on one side, I move by translation back into this chart. Is everyone okay with that? Now, I said a statement about exceptional points. So where do these exceptional points arise? They arise from vertices of these polygons. So let's show that. So if I look at this point that's at the edge between orange and blue, it's at the bottom of blue. So it's got to be the same as this point over here. Is everyone okay with that? And that in turn is the same as this point here. And so since it's on the far right side of red, it's also this point, but it's also the top of blue, so it's this point, and so forth. You'll see that they all are identified, and then you go back to where you started. So in this picture, all 8 of these vertices are identified, and this is a cone point of cone angle 6 pi. Is everybody okay with that? Great. So that's what a translation surface is. Now, I drew you a particular translation surface, but you could draw me another picture of a translation surface quite easily.
So I have a question.
Sure.
Now that you've opened up the question box and haven't turned me off yet. If you go back to your picture with one cone point, could you actually draw that as an immersed surface with those one singularity of angle 3 times around? Is that a standard picture? This has to be immersed in R3 by putting an R4 and pushing down.
Yeah, I'm not sure if you can draw it in R3. I don't know if you can draw a isometric embedding in R3. There's general theorems that tell you which dimensions you can draw these in. I don't know where that takes into effect.
Okay.
Sorry, I can't answer that.
Right, you may mute me soon. Thank you.
Okay. Yeah, that's a natural question. What's the smallest R to the K you can put this in? Yeah, isometrically. Okay, so there's translation surfaces. There's not just one of them. They come in a space. So you could make the blue line be a little bit longer. You can make the blue line be a little bit longer, say, and then the red line would come across like that. So long as you do it in a pair, you would get a different translation surface. Or you could view this vertex here as being a hinge, and you could move the blue lines along the hinge and kind of tilt it a little bit, right? I guess, sorry, I'm mirroring the wrong way. But you could tilt it this way. Does everybody see how you could, in this way, get a family of translation surfaces?
Yeah.
So the moral is that you can get new translation surfaces by wiggling the sides, by deforming the sides. And of course, you want to do this in pairs to keep the identification correct. So you want to deform parallel pairs together. Okay. And in this way, so in our particular example, we would locally be able to perturb them as vectors . 4 vectors in R2. So locally, our space looks like R2 to the 4th. Okay. So what do I mean by that? So you can look at this blue vector, this red vector, the orange vector, and the black vector, and we can locally think about our space of translation surfaces as letting us move these 4 vectors around. Is everybody okay with that? Great. And so these local coordinates have a name. They're not going to, I might say the name 1 or 2 more times, but these are called period coordinates. And these give you coordinates for the space of translation surfaces. Now, it should also be mentioned that as we wiggle, the cone points, the number and cone angles stay constant. The cone points number and angles stay constant. Meaning the total angle along this cone point, as I deform, will stay in the ways I described by deforming the sides, will stay as 6 pi. Excuse me. Does everybody see that? So for example, if I viewed this blue side as being on a hinge and I moved it over this way, this angle would get smaller, but at the same time, this angle would get bigger. And so the total angle around this cone point would stay the same. I mean, the other way to see it is, you would stay in 8 gon. And so the total angle would stay the same. Okay. And so translation surfaces come in types. So spaces of translation surfaces come in.
By the way, Lorenzo had a question.
Oh, yes. Thanks, Lorenzo.
Yeah, he doesn't have a microphone.
Okay. Oh, the 2 points colliding. Okay, so Lorenzo, I used this word locally, and I wanted to sort of avoid all issues about this. This is one particular patch of coordinates. If singularities are coming close to each other, you would go into a different patch of coordinates. And so period coordinates give you local coordinates, and then there are different patches of them. Thanks for this question, Lorenzo. It's a really good question. So spaces of translation surfaces come in families called strata, are stratified. And these are given by the combinatorics of the cone points. By angle of cone point and number of cone points. So this example I did here is the stratum H2. Because the axis angle at the cone point, there is one cone point with 2 times 2 pi axis angle. Gauss-Bonnet tells you this, or actually in this picture, you could do an Euler characteristic argument that this gives you a genus 2 Riemann surface. Now there's another stratum of genus 2 Riemann surfaces called H11, which has 2 cone points, each of which has 1 times 2 pi axis angle. And this is the way these strata are named. Is everybody okay with this? Great. So also connected to what Lorenzo's great question was, is the fact that these spaces, well, these spaces are orbifolds, but they're good orbifolds. And I don't want to talk about the orbifold issues. Good orbifold just means that it has a cover that's a manifold. These spaces are good orbifolds. I'm going to ignore orbifold issues, but they're also non-compact spaces. And one of the issues with non-compactness comes from what Lorenzo was talking about. If there's a vector that connects these 2 cone points together, in this case, this vector, you could start shrinking it down until the cone point is going to be colliding with itself. And that will make you be leaving your strata of translation surfaces. And just as an aside, some of these deformations make you leave compact sets in the moduli space of Riemann surfaces, but some of them don't. Some of them you're just leaving compact sets in whatever your stratum is, but you might be staying in a compact set in the space of Riemann surfaces. This is just an aside, doesn't really show up in the talk, but maybe it's helpful for context to kind of separate the Riemann surface from its additional structure, which is giving you these translation surfaces. Okay, is everyone okay with this?
I have a question about, so for this, you have here, sorry, I'm a little confused about colliding. So the cone points are already identified here. So you're like effectively taking the closed curve there and collapsing it to a point.
It looks like a cusp, I think, right?
Yeah, okay.
It's some sort of cusp in the moduli space.
Yeah, so in this situation, you're leaving compact sets in the space of Riemann surfaces, and what you're going to be going to is some kind of nodal Riemann surface.
I see, okay.
And it would take me a minute or two to draw a picture of what that nodal one looks like, but you can figure out what it would look like.
But he's got a good question, is that if you just identified those points, you'd have another flat surface and it wouldn't be singular. It'd just have fewer vertices, lower genus. So you've got some sort of degeneration from one type of flat surface to another one. Does the way in which you degenerate make any difference on the limit?
So I'm not sure you actually end up with a flat surface in this case in the limit. I think you end up with a nodal Riemann surface with an additional structure on it.
Oh, do you? Oh. So
But it depends on your degeneration. Sometimes so in this case where all of the cone points are identified, this can't happen. But in H11, it's easy to make degenerations which stay in a compact set in the moduli space, and you degenerate from H11 to H2. Various things can happen, and people study these things.
Thank you.
Great. Okay, So this is, so this space is non-compact. It's a good orbifold. It also has a volume form coming from the local R2 to the 4th coordinates. Or more generally, the R2 to the K coordinates, or more generally, R2 to the K. So it's R2 to the 4th in the picture I drew, but more generally, it's going to be R2 to the K, where K is the number of pairs of parallel sides you have, because you're allowed to deform each of those independently as vectors in R2. And this measure can be restricted to unit area translation surfaces. So disintegrated to unit area translation surfaces, or you could do a cone construction. Gives a measure called Maser-Veach measure. Which I think it's natural to think as being the Lebesgue class, because it's given by local coordinates, okay? And, all right. So this is the space of translation surfaces. Any questions on the space of translation surfaces?
So you just take the volume form on this on the coordinate space, and basically that's how you get. So my question is how to write this volume in terms of local coordinates?
It's exactly what you said. It's given locally by viewing your space as being R2 to the, in our case, R2 to the 4th, and you perturb it. Now, for various reasons, it helps to, in this subject, you often want to focus just on unit area translation surfaces. So this is a volume, as a natural volume form on all area translation surfaces, but you can then disintegrate it and get a volume form on unit area translation surfaces, and that's called the Maser-Veach measure. So you get it on all different areas by just this locally deforming it in R2 to the 4th, in the specific case where you're doing, and then you disintegrate it to the unit area case in order to get this Maser-Veach measure. Did I answer you, Stan?
Yeah, thanks.
Thank you. Okay, thank you for that question. Oh, and maybe just to kind of hammer home the picture. So you could, so kind of what's going on here is locally, I want to identify this translation surface with an element of R2 to the 4th. So I just look at the parameters that give me these vectors. So because I drew this picture in Tixi, I know what these vectors are. And so locally, my translation surface would be represented as the following 4-tuple of pairs and 0.6. So I could identify this translation surface locally as being 0.3, 1.3, 0.9, 0, and so forth. So does that make sense to everybody? Right. Okay. Sorry if I took too long there. Okay, so now the next big part of my talk, which once again ties into Steve's very first question at the start of the talk, which is that there's an action of a group on this space. And this group is SL2R. It acts on translation surfaces by acting on the charts. So I just draw my translation surface as a polygon, or maybe a finite set of polygons in the plane that have some kind of identification, and then just use the usual linear action of SL2R on these polygons, and I get what's probably, and I get a new collection of polygons, and I get, and then I do the identifications of them, and that gives me a new translation surface. Okay, I have a question here. Okay, Lorenzo asked a question of whether I'm modding out by rotations or just by rescaling. So I'm not modding out by rotations at all, and I'm not modding out by rescaling. I'm not modding out by either of those things. there is an equivalence relation on translation surfaces, which is given by a differentiable map between them, where the derivative is 1 everywhere. That's called a translation equivalence. And so, for example, to go back to Lorenzo's questions, you could imagine I cut along this triangle here, and then I glue this triangle on over to here to get a picture that looks like that. That's going to be the same translation surface because there's going to be a map between them. It's actually the identity map whose derivative is 1 everywhere. Sometimes you can get other translation equivalences, but those come from very special symmetries of your translation surface. Did I answer your question, Lorenzo? Okay.
Well, I would object. If you
Yes.
won't object, I'll object.
Okay.
Because you just told me you're gonna take a chunk of your space and move it. And then you told me it's the identity. So that's like a 3-card Monte thingy. I mean, you're moving it and you're not moving it. What's up?
Oh, I'm just doing, so in this case, I'm doing just, this is a good question, Steve, thanks for asking it. So all I've done is I've given you a different chart in this case for the same surface, right? So what's my map gonna be like? So at this point here, what would the map be on the other picture? The map would just send this point here, or let's move just a little bit off. It would send, oh, let's do it correctly.
It's not the identity, it's the only point.
It would just be there. It would just be it's just a different chart for the same surface.
Yeah.
Okay.
I mean, because they're identification spaces. But if you're really stickler, it's a different map because you're slicing the map. It's moving the map around on the plane, but it's the same in the identification space.
Which is the space, right? It's a different chart for the same surface. But yeah, are you happy with this, Steve? Or
oh, I'm happy. Yeah,
okay,
yeah.
great.
Oh no, we're having a good time.
Great. Okay, so let's move back to the S. Yeah, so let's move back to this SL2R action on the space of translation surfaces. So it acts by acting on the charts. And then you get a new chart, which usually is for a different translation surface. So for the sake of ease of drawing, because I wanted to draw 2 next to each other that were acted on, I'm drawing sort of a degenerate picture. It turns out that this example is a torus with 2 marked points, but let's ignore that. And so this is a translation surface where, say, the black side's identified to the black side, the brown side's identified to the brown side, and the red side's identified to the red side. And so I just map this by the map 2, 0, 0, 1/2. So that means I contract all of the vertical components by 1/2, and I multiply all of the horizontal components by 2, and I get what's probably a different translation surface. Now, sometimes I can cut up the translation surface that I dealt with and reassemble it to get the one I started with back. But this is a very exceptional situation. Any questions on this? Great. So Steve knows from his first question that I want to talk about the Horocycle flow. And so I want to give you a picture of how the Horocycle flow acts on this chart as well. So if you take this picture here and you act on it by the map 1, 1, 0, 1, you'll get out this translation surface over here. So that's the action of a different subgroup on this space. So is everyone happy about the fact that SL2R acts on this space and how it acts? Great, because this is now the center point for the rest of the talk. So I'm going to begin with some history here. And the history is going to be considered talking about what we know about how different subgroups of SL2R act on this space. So there's a GT action, which is given by e to the t 0, 0, e to the minus t. And this is called the Titular geodesic flow. And I might just call it the geodesic flow, because this gives you parametrized geodesics for the Teichmuller metric on the Riemann on the space of Riemann surfaces. An aside is morally all geodesic rays on this moduli space arise in this way. This is a slight lie. I need to allow slightly more general structures than translation structures. I need your charts to allow yourself have flips also in addition to the translations. So sometimes these are called half translation surfaces. Now, I also need to allow the cone points to have cone angles that are integer multiples of pi, not just integer multiples of 2 pi. But morally, these give you all parametrized Teichmuller geodesics. Okay. And this space is wild and flexible. So the first thing, I've told you one measure already on this space, which is the Maser-Veach measure. And this Maser-Veach measure is GT ergodic. And by Veach, we know that GT is a Bernoulli flow. So it's actually a Bernoulli flow. With respect to this measure. Okay, now there's a ton of other ergodic measures. For example,
excuse me, can you explain how does that matrix act coordinate-wise on the space? You probably explained it on your previous slide, but
no, I didn't. Thank you very much for this question, Stan. So I drew a picture, but that doesn't really show you how it's acting in terms of the coordinates that we've given to this space. But it acts diagonally on the coordinates. So if I'm identifying my translation surface, in this case with 4 pairs in R2, each of these pairs comes from a side that's just sitting in R2 that I'm acting on by this matrix. So the matrix acts diagonally by acting on each of these pairs individually. And that's the way any matrix in SL2R would act on these coordinates. Did that answer your question, Stan?
Yeah, thank you.
Thank you for the question. It was a great question.
Could you remind us what a Bernoulli flow is? Or is that out of the scope?
Oh, let me just, do you mind if I talk for a minute more and then we'll
No,
see
not at all.
Answers? Okay, great. So we have a ton of different ergodic measures also. We have periodic measures. So what do these measures come from? They come from closed GT orbits, right? Surprisingly, these can occur in this space. There also can be measures with any Hausdorff dimension between 1 and the dimension of the unit area locus, of the area 1 locus. So in our situation where we had a space where all of the translation surfaces was like R2 to the 4th, the area 1 condition is a 1-dimensional condition. So this would be a 7-dimensional space. And you can have any Hausdorff dimension between them. And so I'll just say morally why this is true. So morally, the flow occurs on a shift space. So the flow is a suspension flow over a topologically mixing Markov shift. Okay, this is a lie, but it's not very far from being a lie. So you can, by viewing this as a symbolic space, you can build all sorts of funky measures for the shift system. And then from that, you can create measures for you get measures for the suspension flow over it. And that gives you sort of large constructions of kind of all sorts of ergodic measures. And so these Bernoulli, yes?
Is the Markov system you take a boundary piece and look at the return to the boundary?
It's a little complicated. So you
It's not
build a
that simple.
particular transversal to the flow. So morally what's going on here is something called Rosy-Veach induction.
Okay.
Okay, and that has a combinatorial structure to it. And that's where this is coming from.
Okay, thanks.
Okay.
Well, that gives you the shift.
Yes, and in answer to Lorenzo's great question, sorry if I said this unclearly, by Hausdorff dimension, I really mean all numbers between 1 and 7. Okay, and so in answer to Hunter's earlier question, Bernoulli flows, I think, let me get this. So their discrete time maps are measurably isomorphic to product system, to shifts with product measures on them. And there's no there's another condition to rule out something like a constant height suspension flow over those systems. And I forget exactly the right condition. Louis, I know you know the right answer to this.
Yeah.
What's the words I should say?
Well, okay, so a Bernoulli flow is an action of a real line, but you can restrict it to the integers or in fact to any other subgroup of the real line. And whenever you do this, you will get a Bernoulli system, which is a product measure. So it's like the integers acting on a to the z, where a is some finite set or maybe a countable set with a probability measure on it. And so then you're just looking at product measure. The geodesic flow on the unit tangent bundle of a hyperbolic surface is also known to be Bernoulli. So just as a comparison.
What's the condition I'm leaving out? Because if I do a constant height flow over the shift on two symbols, that's not a Bernoulli flow, right?
Right.
What's the condition that I need to say to rule that out? Is it that all of the discrete time maps are ergodic? Is that enough?
Well, just all of the discrete time one maps are already Bernoulli. I mean, that's enough.
Okay. All right. Thanks, Louis. Okay.
So oddly enough, there's only like there's really only two Bernoulli flows up to measure conjugacy and scaling. One with finite entropy and the other with infinite.
Thanks, Louis. So there's a ton of other, okay, so I've just said that there's a ton of other ergodic measures, and even things can get worse. So there's a dense G delta set. Where the GT action equidistributes to Maser-Veach along a subsequence. And I'm a non-compact space, so it equidistributes to the zero measure along a different subsequence. So you can have loss of mass, and it can really be an issue that typical points will see. Right. Now there's another subgroup of this space, which is the upper triangular subgroup. And here, the ergodic measures are very restricted and rigid. Okay. So what do we know about them? So we know that, so we'll give this group a name, it's P. So P ergodic gives you free of charge that your SL2 are ergodic. By free of charge, I mean you quote a big theorem. So anything that's ergodic for this subgroup is ergodic, is invariant for more things. So it's automatically SL2R invariant. So you get additional invariance free of charge. And this is a result of Eskin and Mirzakhani. Okay. There's only a countable number of P ergodic measures. Numbers, only a countable number. Each ergodic measure has nice support. And I won't say much about what nice support means in the coordinates, in the local coordinates. And in fact, it's Lebesgue in these coordinates. Lebesgue in coordinates. So these invariant, these measures are, the supports of these measures locally have restrictions between restrictions on algebraic relations between the various sides. And so that gives you restrictions on the coordinates, and you are Lebesgue in those coordinates. All right. And then let's say one more result. So if mu1 comma dot 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 is a sequence of P ergodic measures, probability measures, any weak star limit is a P ergodic probability measure. Is 2. So there can be no loss of mass in this situation because you preserve that it's probability measure. Okay. And do I have until noon, or just should I stop at 10:50? 11:50?
Noon.
Okay.
I would say noon, yeah.
So let me say one more remark. You have a genericity result, which is that the integral from 0 to t of the integral from 0 to 1 of f of gt us of x. So for all x, there exists nu sub x, so that I converge to the integral of f with respect to nu sub x over the entire space for all continuously compactly supported functions on my space, okay? Where u sub s is equal to 1s01. So this fact that P ergodic implies SL2R ergodic is very helpful to probe the SL2R dynamics, because P is an amenable group where SL2R is not amenable. And this is the type, this is a type of averaging that you can do in P. So this is saying that every point has nice P dynamics for the P subgroup. Is everyone okay with that?
Mm-hmm.
Great. So now, briefly, so this U sub S group, which is 1s01, this is still mysterious. So this began getting studied in detail in the 90s, and it was studied in analogy with homogeneous dynamics. And the news, so homogeneous dynamics means sort of the dynamics of a Lie group modulo a lattice. So you look at, say, SLN R modulo SLN Z, and you want to study the dynamics of various subgroups of SLN R on this space. Okay. And the news started out to be good. So Minsky and Weiss showed that there was no loss of mass. No loss of mass. So various people, so including Eskin, Maser, Eskin, Markloff, Morris, Kalta, Wortman, and Bainbridge, Smiley, and Weiss showed in special circumstances very restricted. Okay, let's say a little bit about what this means. So if you look at how this matrix acts on this picture I drew here, notice that this side here, there's another side here that's also horizontal and has equal length. And that's because matrices of the form 1T, 0, 1 act isometrically on horizontal lines. And so this clearly gives you 1T, 0, 1 invariant sets in your space, and those have to support 1T, 0, 1 ergodic measures. And then the dream would be that the other ones are all SL2R ergodic. Now, this is known to be false by various constructions of Kalta and more advanced constructions of Smiley and Weiss, but all of the known examples in any situation involve taking some additional ones, involve taking something that's SL2R ergodic and perturbing it in a way that plays nicely with the Horocycle flow, but does not play nicely with the rest of SL2R. So you break the SL2R ergodicity while preserving the UT ergodicity. And in fact, you break the SL2R invariance. And then I should also say that minimal sets were classified for topological dynamics, minimal sets classified by Smiley and Weiss. Okay, so, and more recently, there has been some bad news. And the bad news on sort of how restricting or flexible this is, it's mostly about the orbits. But there's also, what I want to talk about today is something we can say about the structure of the invariant measures. So the set of invariant measures. So this is a theorem of myself, Osama Khalil, and John Smiley. And what do we show? That there exists a sequence of UT ergodic measures, which weak star converges to a convex combination of two ergodic measures, SL2R ergodic measures. One of them is the Maser-Veach measure on H2. And so what you should think about this is this has dimension 7. And one is on a closed SL2R orbit. And so it has dimension 3, which is the same as the dimension of SL2R. Okay. Now this cannot happen in the restricted case. The weak star limit of any sequence of p ergodic measures is going to be p ergodic as well. Now this is better than what happens in the case of GT, where really you just have crazy things going on, and you can have measures where you have escape of mass, you can have all sorts of kind of crazy behavior. And so it falls a little bit in between. Are there any questions on the statement of this result?
So just to rephrase it in my head, so the idea is that if you're p-ergodic, any weak star limit of p-ergodic measures is going to be p-ergodic, but that isn't the case if you restrict to further to this UT
Yes.
one parameter subgroup. Okay.
Yeah. Okay, so maybe I should say that as a corollary of this, we show that there exists a dense G delta subgroup, a dense G delta subset of H2. So that the integral of f of ut of x, 1 over t, does not have a limit. For some f in the continuous compactly supported functions on the strata. So this is telling us, so this statement about measures is giving us consequences about the dynamics of points also. I should mention that a similar result was proved by me, John Smiley, and Barak Weiss in H11 by quite different methods that really can't say anything about the structure of the set of invariant measures. Okay. Any questions on the statement of these two results? So in the last oh, sorry, Hunter, did you have a question?
I did, but I can ask after you finish.
Okay. So in the last 5 minutes of the talk or so, I want to say a little bit about how this proof goes. So the first thing to do is to draw you a picture of a special translation surface called the octagon. So the SL2R orbit of the octagon is going to be this funky other closed SL2R orbit. It turns out that this is the SL2R orbit of the octagon is closed in the space of translation surfaces. This is a beautiful discovery of Bill Veach. Now let's look about how dynamics act on the octagon. So if I go off this side, I'm identified down here, and this is a periodic trajectory. And similarly, all of these give you periodic trajectories that go across the bottom, then to the top, then back to where they started. Is everyone okay with that? And that's because, so just to be clear, the identification I'm using is, say, this side here is parallel and of the same length, so it's identified to this side. Now we have another such chain of periodic orbits here. So we have two different periodic cylinders, and they eat up my entire surface. Okay? And it is a computation to show that if you look at 1, 2 plus the square root of 2 applied to each cylinder, it fixes each cylinder. It sends each cylinder back to itself. So if I look at the pink picture, what's going to happen is this side here will get sent all the way over to here, and my cylinder will look like this, but I can cut it along this side and glue it back to where it was beforehand. So this map is not the identity on the cylinder, but it maps the cylinder to itself. Is everybody okay with that? And the same thing is true, just a tiny bit more complicated, of the picture in green. Okay. So I have a family of UT periodic orbits. The first one comes from this octagon surface, O, the octagon. Is 1 is 2 plus the square root of 2 periodic. Okay, but what I can do, because I understood this by looking at the two cylinders independently, I can deform one of the cylinders while keeping the other one the same. So what I've done is I've fixed the green cylinder and I've deformed the pink cylinder. And I deformed it, in this case, by multiplying it by 1101 times pink cylinder. Okay. And I obtain a new 2 plus square root of 2 periodic surface. So by deforming one cylinder, say pink, and fixing the other, I get a 1-parameter family. Of such periodic US orbits. Okay. So there's one more key ingredient, which is how GT acts with US. So if you look, that GT US is equal to U e to the 2t times S GT. So GT of the octagon is e to the 2t times 2 plus the square root of 2 periodic. Okay. So what we do is we push forward this whole family by GT. And we study this family using the derivative of the GT action, and study it. And so I think I have time to say one last key result. So what's the big theorem we prove? So the main theorem we prove is the following thing, that for all epsilon bigger than 0, for all t big enough, there exists a constant c sub t, so that if I look at the set of s's that I care about, so that's between 0 and 2 plus the square root of 2, and I want to look at the norm of the derivative of the geodesic flow for time t, and I want to evaluate this at US of my octagon surface, and I want this to be bigger than c sub t, this is at least 0.1. And if I want this to be less than epsilon times c sub t, this is also at least 0.1. Okay? So the derivative of the geodesic flow fluctuates wildly along this Horocycle. So when I push forward this family, and then I look at how the family varies, it varies wildly. At some points, you're sent very quickly away from the locus, and at other points, you hug the locus very tightly. Right? And by doing a little bit more work, you're able to produce a family of measures as in the statement of the theorem. So in particular, this sequence of UT ergodic measures are all UT periodic measures with longer and longer periods. Okay, thank you for the time.
Yeah, so let's thank Jon. Great, so yeah, I'll just open it up for questions. If you have a question, just unmute yourself.
So I have a question about the corollary. Is G delta dependent on the F? Sorry, is the G delta subset dependent on the F?
You can pick one F and you can find a G delta subset that works for that one F.
Okay. I have another question.
Sure.
So for the GT flow, you said that you have loss of mass. So I'm trying to understand this. Like, is this like it's like I'm trying to picture the GT orbit or the GT action pushing the measures support out to the boundary of the stratum. Is that what I should be thinking, or like to the like to cusps where there's very little air measure? Maybe I'm not thinking of this the right way. I'm just trying to pick.
I'm sorry. So I hope I didn't say anything wrong, but I think the best way to think about it is for individual points. If you have a point that has a vertical saddle connection, a vertical trajectory between two singular points, GT is going to pinch that, and we're going to leave compact sets in our space because of that.
I see. Yeah. Okay.
And then, of course, if you had an almost vertical trajectory, you would leave compact sets for a long time, and then maybe you'd come back. But then maybe you have an even longer trajectory that's even more close to the vertical. And this could repeat over and over again. And on a dense G delta set, so a set that's large in the sense of point set topology or the Baire category theorem, there'll be a subsequence where this, along which you've lost mass. Did I answer your question, Hunter?
Yeah, I think so. Yeah.
No, I think he asked where the mass went.
It leaves the space.
Oh, okay.
Yeah.
Just pushes up.
Oh, Jeff had a question about what the Hausdorff dimension of the measures are. So a couple of things. This is a great question. Thanks, Jeff, for it. So the sequence that's Wick-Star converging to this weird object. So the sequence, those all have Hausdorff dimension 1 because they're just periodic Horocycle orbits. It looks like a circle in my space. Now, the limit has Hausdorff dimension 7, and that comes from the component that's Maser-Veach. Okay. However, it's an open question of whether there's a UT ergodic measure that has intermediate Hausdorff dimension, so non-integer Hausdorff dimension. And I think that's a very interesting question. And I think the community would be extremely excited by an example that didn't have that, or a result that said they all had to. Did that answer your question, Jeff? It's a great question.
I'm wondering, how does this result compare with your result with Weiss and Smiley? With Barak, Weiss, and Smiley about, I don't remember entirely, but I thought that one was saying that you have a UT ergodic measure, which is not SL2R invariant, but I thought that there was something about Hausdorff dimension of the measure.
Yeah, thank you very much for this question. So my work with Smiley and Weiss is really all about the topological dynamics. So we build a weird orbit closure of Hausdorff dimension between 5 halves and 6. that's greater than or equal to 5/2 and strictly less than 6. We do not build weird ergodic measures, though we do prove non-genericity results of points. And our methods rely on very special things coming from the translation flow. So this flat dynamical system that happens on a translation surface. And the behaviors we use are really rare behaviors. They have positive Hausdorff codimension. And there's so this sort of gives you heuristic reasons for thinking that these kinds of arguments can't probe the invariant measures. Though it can say interesting things about the topological dynamics.
Okay.
And to compare that, so the kind of statement we do here is really saying something about the typical behavior of orbits. These fluctuations are things that are typically seen. And so heuristically, that's why there might be hope that such results can sort of probe a little bit about the structure of invariant measures. And of course, as Jeff was pointing out, we can't really build any weird ergodic measures, but we can say that the structure of the set of them is weird in such a way that has certain dynamical consequences. Did I answer your question, Louis, or did I just dodge it entirely?
No, that's good, right? I mean, so you don't know whether you have, for example, an ergodic measure that has full support on this weird orbit closure.
Oh, I think we can rule those out because of this situation is very, very special. And the typical points on this actually, so what this looks like, it's a really weird example. It looks like you've got a 5-dimensional set and you kind of deform it in weird, along a weird fractal to build a bigger set. And the things you've added by deforming it, most of them spend most of their life on the nice object that you didn't deform before the deforming.
Okay.
Yeah, sorry, I can't say more about it in this time.
Yeah, that's good. Yeah, other questions? Well, yeah.
Oh, sorry, just what, so maybe you already said this, but how again do you build the ergodic measures from these orbits? Do you just like push forward the Lebesgue measure on S, like on the one parameter subgroup, or how do you get the ergodic measures?
Oh, yeah, so in this, so let me see if I get where your question is happening correctly. So your question is on the statement of our main theorem. We're talking about a weak star limit of ergodic measures. And I told you that those that particular one were all periodicized. And you're asking how does the periodicity give you an ergodic measure? Is that correct?
Yeah.
Okay, so this is a periodic orbit. So the dynamics looks like you run around a circle at constant speed, and then you end up back where you started. So you just want to put on the uniform mass you get from the dynamics along the circle.
Okay.
Did that answer your question, Hunter?
I think so, yeah. Yeah, because it's just a circle, yeah. Okay.